we shall be looking at application of WRONSKIAN. WRONSKIAN application in second order differential equation non-homogeneous. For example, when we have y prime prime plus y is equal to sec x is equal to sec x. Y prime prime plus y equal to sec x. This implies the square y x squared plus y equal to 1 over cos x in the solution process. Now, this is non-homogeneous second order differential equation, but you cannot use undetermined coefficient to solve it easily. You can either use the variation of parameter method or the WRONSKIAN method. So we are going to use the WRONSKIAN method. The WRONSKIAN method, as it stands, is basically minus y1 integral y2 r function of x differential x divided by WRONSKIAN y1 y2 plus y2 integral y1 r function of x differential x WRONSKIAN of y1 y2. You see, this is the y particular expression where we have the WRONSKIAN and the WRONSKIAN factor here. Now take note that this relationship as it stands can be used to get the particular part of it. Okay, let us make the equation an homogeneous equation to get the complementary factor solution expression. That is to say, from the first question, we will now be having let the square y dx squared plus y equal to 0. You make the equation homogeneous. When the equation is homogeneous, then you are now going to translate the homogeneous equation into what we call the auxiliary equation. Let also the y dx equal to 5. If the y dx is equal to 5, it therefore means that the auxiliary equation is 5 squared plus 1 equal to 0. Now we get that this 5 squared is equal to minus 1 when it crosses to the other side. So that at the end of the day, 5 is equal to 5, 1, 2 is equal to plus minus root of minus 1. Now, if it is this, then furthermore, this is going to give us 5, 1, 2 is equal to plus minus j, the imaginary. Because the square root of minus 1 is 1j. Now, take note that the connotation of this expression can be implied with respect to an homogeneous relationship of a complementary function solution, which is y complementary is equal to now unknown translated to give us the actual relationship of this when it is trigonometrical gives you y complementary equal to c1 cos 1x, which is x, because 1 is the imaginary part and the real part is 0, which is exponential 0 to cover up with this one, plus c2 sine 1x, which is sine x. This is the solution format for the second order differential equation homogeneous that was extracted from the non-homogeneous expression that required the application of WRONSKIAN to resolve the final answer. We are done with the complementary function part, which is the homogeneous part. We have to proceed to the WRONSKIAN application. Basically, the concept of WRONSKIAN is that y1 is equal to cos x, y2 is equal to sine x. Take note. y1 equal to cos x and y2 is equal to sine x. So when this is to be utilized in the WRONSKIAN relationship for the particular expression, therefore y particular, from here now, you see the relationship, y particular is equal to minus y1 is cos x, integral of y2. y2 is the second part, which is sine x. Take note. Multiply by RS. RS is secant x at the other side, the right hand side. And secant x implies 1 over cos x. Multiply by 1 over cos x. Differential x. Without the derivative, you cannot integrate. Divided by the WRONSKIAN. y1 comma y2 plus the other value, which is y2 sine x, integral y1, which is cos x, multiplied by this other side, the value at the right hand side, reciprocal of cos x. Differential x over, you divide by WRONSKIAN. Take note, you now divide by WRONSKIAN. 1 over cos x divided by WRONSKIAN, function of y1, y2. We are to perform the WRONSKIAN test. WRONSKIAN test, W, function of y1, y2 is equal to the determinant expression of cos x sine x. Yes, cos x sine x. Now, derivative of cos x is minus sine x. Derivative of sine x is cos x. When you have performed the WRONSKIAN analysis, which is the determinant, 2 by 2 determinant, application of matrices. WRONSKIAN uses matrices to get the final value. So at this point, we are going to have cos square. We're going to get cos square of x plus sine square of x. That is to say, cos x multiply cos x to get cos square x minus sine x times sine x to give you plus sine 2x. Sine square x rather, please. Now, in trigonometrical identity based on Abel-Weber relationship in trigonometry, cos square x plus sine square x is equal to 1. Take note. So that this relationship above can further be simplified by inducing the WRONSKIAN values. When the WRONSKIAN values are induced, on this equation, we now have y particular is equal to minus cos of x integral of, this is 1, of course, so you will now be having tan x, differential x, because sine x over cos x is equal to tan x. Remember that the WRONSKIAN is over 1. WRONSKIAN of y1 comma y2 is 1, which we have just derived from this WRONSKIAN analysis. Now plus, this is going to give you x sine x, because cos x cancel cos x to give you 1. Integral of dx gives you x. WRONSKIAN is 1. When divided, you have all over 1. So, and anything over 1 remains the same thing. So cos x cancel cos x to give you 1 dx, to give you integral dx is x, to multiply sine x to give you x sine x. So also is this tan x dx. Now, the y particular is going to give us minus cos of x tan x. This will give you the same thing as cos x, absolute value of natural log ln cos x. We are going to have it as absolute value of ln cos x. Why? Take note that the relationship of integral tan x dx, integral tan x dx gives us integral of sine x over cos x, differential x. So if this is to go by, based on the trigonometrical identity resolution, we now have the derivative of this gives minus sine x. So you require another minus here. And of course, the expression, when we move it out with a negative sign, which is here, because what you are having in natural sense is minus cos of x from here. Now, if this goes in, you will now be having the minus here and the cos of x here. So if we differentiate cos x, you get minus sin x. It means that this is now going to give us cos x ln natural log of cos x. That's it. Take note of the integration method that gave us this value plus x sine x. So if this is a particular, the total relationship, final answer will be given us y total is equal to y homogeneous, y complementary plus y particular. And the y complementary is C1 cos x plus C2 sin x. That is, we are inserting the homogeneous solution, which is the first complementary function solution, as y total, as you know, that y total in a differential equation is equal to the y complementary plus y particular. So the complementary part is what we have inserted here, plus the y particular, the particular part of it, which is from here to here. Y particular will now give you plus cos x, then ln natural log of cos x. Natural log of cos x, absolute value, because we require positive values. That is why it has to be absolute. For the natural logarithmic expression to be positive, plus x sine x. Now, this entity, the last expression, is the final answer for the question y prime prime plus y equal to sec x. So we have solved the homogeneous part, which is this part, that we use the auxiliary equation y squared plus 1 equal to 0. We got our imaginary roots and translate it to trigonometrical form for the complementary function solution. Then we have to use the WRONSKIAN formula to get the y particular, which is minus y1 integral y2 r function of x, which is the right hand side value, differential x divided by WRONSKIAN y1 y2 plus y2 integral y1 r function of x differential s over WRONSKIAN 1 and 2, which we now discover that the WRONSKIAN value was 1. How? This is y1, this is y2, y1, y2. Differentiate cos x minus sin x. Differentiate sin x cos x. Now, find the determinant of this. We have cos square x, which is here. We now cross multiply by subtraction. We now have plus, because there is already a minus, and there is minus in between here to give you plus sin square x, which is equal to 1. Now, the log of this relationship in trigonometry is that cos square x sin square x is equal to 1. So that is to say the WRONSKIAN is 1. So we now have placement of 1 here. Take note. Take note that this relationship, the 1 automatically over time will disappear. Yes, because the WRONSKIAN tan s over 1 is tan s. X sin x over 1 is x sin x. How do we get x sin x? Because cos s cancel cos s, so we have 1. Integral ds is x. Bring it out here. Now, integral of tan x was what I clarified here. In fact, it will be better when you attach minus cos s integral tan s ds. So when we bring it here for clarification, we have minus cos s integral tan s ds to give you the derivative of cos s is minus sin s. So shift the negative sign inside to make it conspicuous that the derivative of cos s is minus sin s, and that gives you the natural log of the denominator for the integration. And that is how we got cos x ln cos s plus x sin x. Progressively, y total of a second order differential equation non-homogeneous is complementary function plus particular function. The complementary function solution, which is the homogeneous solution, is C1 cos x plus C2 sin x. Now, the particular solution that we got is cos x ln cos x plus x sin x. Remember, this entity was just this part, which is minus cos x integral tan x dx. So this is the final answer to the non-homogeneous second order differential equation solvable by WRONSKIAN methodology. Take note.